So the way we use these alpha and beta functions in describing orbitals is that, so for example, if we have a 1s electron in hydrogen or helium or whatever, and it's a spin-up electron, the way we keep track of this is that we have our 1s wave function and we multiply it by the alpha spin function. All right, and so we can have 1s psi 1s alpha, psi 1s beta, right? That would be our 1s electron that's spin up here and 1s electron that's spin down here. One key thing is that the alpha and beta functions are orthonormal, or they're orthogonal, and we assume that they're normalized as well, or we treat them as normalized. So if we take, for example, if we integrate over psi 1s alpha star, right? If we look at the problem, if we do this integral where we have psi 1s alpha and psi 1s beta, we can separate this out over d tau. We can separate this out into an integral over just the spatial parts. And this integral would give us 1, because we'll assume these are normalized. But our integral of alpha star beta, because they're orthogonal, this will give us 0. And so overall, this integral is 0. Okay. So we can use this to write orbitals for helium, right? So to sort of label the orbitals that we'll get for helium. So if we're thinking about our two 1s electrons, our total wave function, this is a capital psi, because we're going to have lowercase si's to represent our two, individual electron wave functions. This is looking at both electrons at the same time. Ours is going to be a product of our 1s wave function for electron 1 spin up, and a 1s electron for the spin down electron, which we'll call electron 2. So we'll have, the important thing is we have one of each spin. Now it turns out there's actually a problem here. So the problem is that we can't distinguish between our two electrons. And that's a fundamental property of electrons and of particles in general. So we can't tell whether electron 1 is the spin-up electron or the spin-down electron. And so mathematically, we have to consider both cases where electron 1 is the spin-up electron or electron 1 is the spin-down electron. And so what we do is we write this as a combination of those two cases. Mathematically, this is the way we deal with this. So we have two options. We can have one combination where our two options add together. So we have 1s alpha, parentheses in the wrong place, 1s alpha 1, 1s beta 2, and then we have the opposite, 1s alpha 2, 1s beta 1, right? And so we swapped which electron is which, and we just add these together. Or we can subtract them, right? Mathematically, it doesn't really matter whether we add or subtract them. So we can have the other option that we have 1s alpha 1, 1s beta 2, minus 1s alpha 2, 1s beta 1, right? And we have to do this because the electrons are indistinguishable, and this is a fundamental property of them. So the question is, do we use both of these? Is there just one of these we can use? And this comes back to the fundamental properties of our two types of particles that I talked about in a previous video, fermions and bosons. Again, remember, fermions are half-integer spin particles, and bosons are whole-integer spin particles. And the reason we make this distinction is because fermions and bosons have very different fundamental properties. All right, so fermions, their wave functions that describe these particles, they must be antisymmetric. With respect to exchange of particles. So if we have two fermions and we swap which one is 1 and 2, the wave function sign should change. It should go from positive to negative. Not should, has to. It has to go from positive to negative. So to write this out mathematically, if we have a wave function that, say, depends on two particles, if we swap the identity of particle 1 and particle 2, the wave function should change sign, has to change sign. For bosons, it's the opposite. So bosons, the wave functions must be symmetric with respect to exchange of particles. Right, caught up with my writing. All right, and so since electrons are fermions, they have to obey this anti-symmetry. If, for example, we had photons instead, they would obey the opposite. They would be symmetric. So because electrons are fermions, only the second choice of our two choices above, let me go back to those, right, of our total wave functions here, only the second choice satisfies the property that if we swap 1 and 2, the sign changes for our wave function. Right, and so this has to be, for fermions, this is the only one that works. For bosons, it's the opposite. If we were dealing with two bosons instead of fermions, only this wave function, this combination of our spins would work, of adding them together instead of subtracting them. And so it's the only choice that works, and we can show that explicitly if we switch 1 and 2, the sign changes for it.